Hi guys, in this second video on acid-base chemistry, let's take a look at bases. Now bases are said to accept a proton, H+. But I will tell you that I do not recommend using that terminology. Instead of accept, I would say, let's say bases take an H+. This is more of an action verb. They do something. I've referred to this before, like a thief takes your bicycle. You do not want to say, or you would never say, a thief accepts your bicycle. Take, bases take. This will help you think mechanistically. Now we can also make statements like this. I think such a statement will make more sense after we kind of move along and you look back. Here's a standard acid-base reaction. This carbon anion, methyl carbanion acting as a base and taking an H from water. Now, mechanism. We showed the acid-base mechanism before. It's just one mechanism, two arrows. You need to know it. You have certainly reviewed it, right? Mechanism here. What does the base do? The basic atom makes bond to H. We can say it takes the H. The basic atom now has the H. Same thing here. Now, when I first drew this, I was not exactly as precise as I should have been. I like to circle the lone pair, and then from there an arrow coming, and so we can draw an arrow to the H, like we did back over here. Okay, our standard mechanism. Then the bond between H and some other atom, these electrons move on to that other atom and become, in this case, the third lone pair. And now that carbon is bonded to an H, it has taken an H. The two electrons here in this bonding pair used to be a lone pair on the carbon. And typical, the anion became neutral and the neutral became charged. Or we could say it the other way, the charge became neutral, the neutral became charged. And that's some free information. Again, I gave you sort of tidbits about this in the back. Miscellaneous points to remember. There's about, how many? About 8 or at least sort of comments, things to keep in mind back there. Okay. Now, I say lithium here. This anion has to have a cation. I did not show the cation. Often with carbanions, the cation is lithium plus. And so that lithium would sit here, and then over here it sits with the hydroxide. And so you're going to be making lithium hydroxide. Okay. Now, in any acid-base reaction, the spectator ions may be shown or they may not be. Of course, you knew that coming from Gen Chem. If they are shown, it may be shown like this. And of course, when you see something like this, you know this is lithium plus and hydroxide minus, because you can recognize a salt and you know this is ionic. Another just comment, strong bases will have a higher pKa for the conjugate acid. Yes, this is a pretty strong base, because that carbanion is not that stable. It's going to want to take an H. We can see that from the pKa being very high for the conjugate acid. It means it's not that acidic. Not that acidic. It means it doesn't want to come back this way. If we showed an equilibrium, the equilibrium back this way is going to be very small. Very small. Basically, it's really zero. Okay, that is, this anion wants to take an H badly and end up over here on the right. On the other hand, this minus does not want to take an H and come this way. It's just not going to do it. So this is a weaker base than this one over here. Okay, we'll do more predicting of equilibrium. I know you looked at that a lot in your Gen Chem 2 course. Okay, so what is a base though? We can make this general statement. Bases don't have to be anions. Up here it was an anion. They do not have to be an anion though. Many neutral nitrogens are actually basic. We'll make a note of that. Ultimately, a base is something they have high electron density. Okay? Well, they're going to have a lone pair. Any Bronsted-Lowry base has a lone pair. But higher electron density, the better. Okay? And this can be broadened out to other things. We'll do that a little bit later. Let's start with that. Also, electrons, let's say this, high electron availability. These kind of go hand in hand, but a little bit different here. I'll explain. Okay. Down here we have a neutral amine. It's actually a fairly decent base, even though it's neutral. Now it's not as strong as the one above, because that's an anion. An anion is certainly going to be attracted to the partial plus proton there. But neutral amines do tend to be basic. Here, let's circle this lone pair. Standard acid-base mechanism. Nitrogen takes the H. Electrons move on to oxygen to become third lone pair. That's now minus. The nitrogen now has 4 bonds to H. I drew that condensed. That's just nitrogen with four sigma bonds. The nitrogen is now positive. You can do a formal charge determination. And we have a standard acid-base reaction. We also have pKa's given. pKa for water is about 16. Remember your pKa list, we referred to this before. Water and alcohol is about 16. Okay, here, alcohol but also water. The conjugate acid, the ammonium, it's called, has a pK of about 10. Yeah, that's in the table as well. I believe somewhere, I think it's a side note. Yeah, it's actually, didn't list it up here, but down here, sp3 amines as bases have a pK of about 10. Okay, that's what I showed here. And so again, we see a neutral nitrogen acting as a base. Now actually, I'll go ahead and turn to the next page. In nature, lots of natural products that contain basic nitrogens. All right. These are known as alkaloids. What does oid mean? What's a humanoid? Human-like? Alkaloid, they're alkaline-like, they're basic-like, because they have a basic nitrogen. Each of these natural products contains a basic nitrogen. They're each called alkaloids. That's a general term you need to know, general class of natural products. You may have heard that in your biology courses. LSD is an alkaloid. Okay, it's an ergot alkaloid. That's a specialized type. Has a basic nitrogen. Which nitrogen of LSD is basic? Okay, well, you can pause the video. All right, Hopefully you always want to answer your question yourself, not get an answer from someone else. That way you can go through the process of coming up with your own answer. And the basic nitrogen is here because LP, the lone pair, is in a hybrid orbital, where the other two lone pairs are in p orbitals, not basic. But each of these compounds has a basic nitrogen, and these are some of these are quite unique. Strychnine, sort of a biologically important compound. It's very toxic. Morphine, quinine, the original anti-malarial drug. And then from that, synthetic drugs were developed, including the one on your cover of the workbook, chloroquine. That's a synthetic drug, but it has similarities to quinine, a natural product. Nicotine, it's an alkaloid. One of these nitrogens is more basic than the other. Make sure you know which is most basic. Okay, so a class of natural products there. Well, let's predict some base strengths. Which is stronger, ammonia or methylamine, it's called? Keep in mind, high electron density is best for bases. Each nitrogen has a lone pair, but which lone pair has the highest electron density? And the difference here is this methyl group. What does a methyl group do electronically? If you remember from the last video, an sp3 carbon donates how? Inductively. And that's going to push electron density towards this nitrogen lone pair area. We can consider that sort of the electron density of that lone pair. Over here, I wish I'd have drawn that a little bit bigger to see the difference, but it is larger. More electron density due to the inductive donation by the methyl group, and this is your strongest base. All right, let's try number 2. Nitrogen lone pair, are they the same? What's the difference here? They both have a carbon attached, although this one's sp3. sp3 donates by induction. sp2 carbon actually does not donate by induction, so that actually may give you the answer. But the bigger answer here is hybridization. This lone pair is in an sp3 orbital, and this lone pair is in a sp2 orbital. And thus, which is most basic? This one's most basic. Why? Similar argument we used before with hybridization, but we're sort of reversing it. sp2, that means it is 33% S. Over here, this is 25% S. Which lone pair is closer to the nucleus? This one. LP closer to the nucleus. Closer to mama. Closer to that positively charged nucleus. These electrons are held tighter. They're less available. These electrons are further out. They're more available. And this is an example of better bases are going to have electrons that are more available. That's sort of my explanation, my terminology. All right, so understanding percent S character helps you understand this. The closer those negatively charged electrons are to the positively charged protons, the lower the energy of the lone pair, the more sort of quenched that charge separation is. They're not out there sort of by themselves looking to find a positive charge. They've sort of found it by coming closer to the nucleus. They're not as basic as these guys over here. Number 3. Well, this one's pretty easy if you remember what we said before. This lone pair is sp3 and this lone pair is p orbital. Because there's a p orbital next door and the nitrogen is not currently using the p orbital. This is not like this over here. Over here there's also a p orbital next door, but here the nitrogen has a p orbital. It's already interacting. Here though is when this lone pair is going to want to move into a p orbital and be conjugated. This lone pair is not conjugated. Okay. And when the lone pair is conjugated, we say it's not basic, not reactive. It's busy doing p orbital overlap. This is the basic one. All right. And sp3 nitrogen is, all three circled are sp3. That one's also sp3, but there was a difference here. sp3 nitrogens tend to be your most basic. Okay. Now an sp2 nitrogen can also be slightly basic, but it's not going to be as basic as an sp3. Number 4. Well, these are not nitrogens. Which halide is more basic? We could also maybe, well, let's see if we can answer this. Which one is more basic? Well, it's F minus. It's more basic. Here, it's really because the Cl minus is most stable. Reason it's most stable, remember, because it is larger. The lone pairs are more stable, we can say. And really that's the same thing up here. See, that lone pair is it's stabilized by resonance. That's why it's not a good base. This lone pair is stabilized by being, this one is stabilized by being in a hybrid orbital that has more S character. This is really, I don't see how you can say that that's more stabilized. This is more of a high electron density argument. Well, we could say that because of the higher electron density, it's destabilized, but I typically will not sort of explain it that way. Just simply the increased electron density will get you the answer here. Over here, it's more stable. Number 5, ammonia or water, which is more basic? Well, the lone pair is on different atoms. The fact that there's 2 lone pairs there means nothing. This is a difference in atom. We can look at differences in electronegativity. Oxygen is more electronegative. That means it holds the lone pair tighter. Okay? It's not a hybridization effect making the lone pair be closer to the nucleus. It's the electronegativity making the electrons be closer to the nucleus. And of course, electronegativity ultimately arises because the nucleus has more protons. And so the electrons are more attracted and held closer to the nucleus. And so over here, this is most basic. Because the oxygen is more electronegative, that means that the nitrogen is not as electronegative. We can say it's a worse parent. It doesn't hold its lone pair as tight. It lets its lone pair get out there and react with the H+. We can say electrons more available. Which carbanion is more basic? What's the difference? They both are carbons. They both have the same hybridization. The difference is this has extra alkyl groups and it donates. What's that going to do? Electron density here, electron density here. Increases the electron density. More electron density is going to make this carbanion more basic. We can predict that. Now the basicity is pretty darn similar, but this one is going to be theoretically and in practice slightly more basic. Okay, we're looking for bases, we're looking for high electron density, electron availability. Very often they're anions, okay? Hydroxide is a decent base, is an anion. Carbanion basic, but it can be neutral, and most commonly common atoms, neutral atoms are nitrogens, like ammonia. And again, I showed you many neutral compounds over here that have basic properties. Alkaloids. Cocaine is an alkaloid. Basic nitrogen, couple of esters, benzene ring, classical organic compound. Okay, let's look at predicting equilibrium. Well, before we do that, maybe let's look back over here. And did we have to decide? Back over here. We got a strong acid. Which atom in tramadol is the most basic? Hopefully you can now answer that pretty easily and now show the product. And the product, you want to make sure you use your acid-base mechanism to predict that product. So, give that a try if you have not already. Equilibrium of acid-base reactions. Hopefully this is a good bit of review from your Gen Chem. Reaction will favor the side with the weakest acid. Here again, the methyl anion reacting with water. We need to know the acids on each side. The acid over here is water. It contains the proton that gets exchanged. You might want to say it donates the proton, but again, I would not say it donates the proton. Just like you don't donate your bicycle to the thief. Maybe you can say it kind of supplies the proton, or this. It's the proton that gets taken. Over here, which proton gets taken to come back over here? Well, it's one of these, because one of these has to get taken to become this. That's the acid on this side. It has a pK of about 16, remember? Methane is very weakly acidic. It's virtually not acidic. pKa is greater than 40. Which is the weakest acid? Higher pKa equals weaker acid. So this side is favored. By how much? Well, you should know it's a difference in your pKa's. The difference here is 24 log. So difference of 10 to 24. And so the equilibrium lies to the right by, that's a big number, that's like 100 gazillion. Okay? So at equilibrium you have 1 on that side and 10 to the 24 over there. That side is favored. Huge. Okay? I drew equilibrium here, but this is, I mean, you can almost just get rid of that. Let's look at the next one. Here we have acetic acid plus water. Now here the acetic acid is the acid. Well, it makes sense, acetic acid. That's the H that gets taken because it's gone now. And water must be acting as a base. It took it. That's condensed. Need to show that out. The oxygen only has one pair, one lone pair. Acetic acid is a carboxylic acid, has a pKa of about 5. Okay. Yeah. Hydronium ion is sometimes varies in textbooks. I'm going to say less than 0. Not water. Water is 16. Hydronium ion is less than 0. Which side's favored? This side is favored. It's got the weakest acid. By how much? Difference? Well, we have to assume that's 0. The difference is 10 to the 5. This side is favored by, well, 10 to the 5 is 100,000. Is that right? Yeah. So at equilibrium, this side is favored. So it's 100,000 to 1. Think about that. For every 100,000 molecules of acetic acid placed into water, only one of them will become an ion. 100,000 essentially will remain in the neutral form. So essentially acetic acid is not fully ionizing when put in water. Only if 1 out of 100,000 is ionizing. Now this looks like a pretty weak acid, right? And indeed, that's sort of the definition of a weak acid. It only partially ionizes. Okay. Predicting equilibrium. Now there's some here for you to do on your own. Let's maybe try the first one. This molecule here, known as succinimide, has a pK of 8. And then hydroxide. Please show the products of this acid-base reaction. Then predict which side will be favored and by how much. Now I'll give you the pKa for the acid on the left. You need to come up with the pKa for the acid on the right. The next one, same thing for all of these. I'll give you the pKa for this molecule. These are nitro groups, by the way. They were not on the functional group list for organic 1. You will see nitro groups in organic 2. They're actually fairly common on benzene rings, aromatic rings. This compound, by the way, is called picric acid. It's actually explosive. It's actually quite similar to TNT, if you want to look that up. And for a phenol, it's quite acidic. pKa of about 1. In my table, I told you phenols are typically about 8 to 10. Can be lower though. With these three groups, it really lowers the pKa. This is a tertiary amine, pKa of about 10. We got to be careful though. I want to comment on this. I should have wrote that up here. What does pKa refer to? Okay. Think about that. Down here. Well, that's just phenol, plain phenol. There's no nitro groups on it. Its pKa is about 10. This compound is known as pyridine. We'll see that in organic too. It's actually a fairly common molecule in the lab. It's a little bit toxic, but same thing down here. Show products, predict which side is favored and by how much. And then the last one down here got cut off. This is just NH2. The acid and the base are within the same molecule. That does not matter. These two molecules up here could be connected by a covalent bond. It doesn't affect the chemistry. We can still show the product. Now you may also want to show mechanism here. Now any of these mechanisms can be, again here, this is intermolecular, one molecule reacting with another. While the acid and base could react down here intramolecularly, it could also interact or react inter. That is, the base of one molecule can take the acid proton of another. But you would still end up with the same product either way you go, inter or intramolecular. This example down here also illustrates the acid-base chemistry of an alpha amino acid, which are the building blocks for proteins in human biochemistry. So very important to understand the acid-base reaction and chemistry of amino acids. And when you move on to biochemistry, you'll certainly do that a good bit. So we're trying to lay the foundation here. Okay, so please try these on your own, and we'll work these in class at some point, or based on your questions. All right. You know, actually, I'm going to go ahead and do the first one for you. All right, just to do one. What's the base here? What's the acid? I gave you a pKa that may indicate that it's the acid. That's an anion. Bases are often anions. Hydroxide we sort of know is a base. Let's show an outcome and just let's judge the equilibrium. What's the most acidic H in this molecule? CH or NH? Where would you rather make anion here, on carbon or nitrogen? I think on nitrogen. It would also be resonance stabilized. These electrons bond to the H. These electrons move on to nitrogen. There's one lone pair to begin with. When these electrons move on to nitrogen, we get a second lone pair and we end up with this here, and that nitrogen is now minus. And then what are we making here? One lone pair bonding to oxygen, two lone pairs remaining. So we make this anion and then neutral water. Seems like a standard acid-base outcome. Identified the most basic atom over here and the most acidic proton over here. The acid over here is this molecule, pKa of 8. Acid over here is this molecule, pKa of 16. Water. Which side's favored? 8 or 16? Weakest acid? That would be 16. So this side over here is favored. By how much? Difference, that's 10 to the 8. Which is, what, 100 million? So at equilibrium you have one of these and 10 to the 8 of these. That is one of this side and 10 to the 8 of this. Question. Is hydroxide strong enough of a base to deprotonate succinimide? My question is really, is this reaction going to take place and will it go to the products? Well, the answer is yes. 1 out of every 100 million will be like this. You've turned that into a percentage, it's probably about 99.999999%. That's pretty much a complete reaction. If you get over about 10 to the 2 or 10 to the 3, we can start calling it a complete reaction. I mean, if it's 99.99% done, you can pretty much say it's complete. Anything else to say up here? Now, we didn't have to, but we can look at this. This is a very stable nitrogen anion. It's stabilized by resonance because one of the lone pairs here is in a p orbital, and that really stabilizes this. And that's actually why this NH compound is fairly acidic, where usually NH compounds are not as acidic. But really we're looking at numbers here. We're also looking at our standard acid-base mechanism to predict this. Very often I'll see students who show this product, but then for some reason don't have two lone pairs there. They only have one. Well, if you know it had one to begin with, and you know in the mechanism this moved on to become another lone pair, you should know that it has two. And of course that's a negative charge because you should be able to determine charges. Okay, please give the others a try, and we got to think about what these pKa's mean here for this. All right, let's move ahead. What about pH? How will an acid or base primarily exist at a certain pH? Well, the Henderson-Hasselbalch equation can help answer this, and here it is here. Bam! That's a good looking equation. pH equals pKa plus the log of the basic species over the acidic species. Concentration brackets, the concentration of each. Now, if you do this math, okay, you will see in summary that if the pH is greater than the pKa, then the basic species will predominate. But if the pH is less than the pKa, A will predominate. We can see that because, for example, if the basic concentration was 10 and the acidic concentration was 1, just sort of random numbers, no units, log of 10 is 1. Well, if that's 1, then the pH is going to be greater than the pKa, because pKa plus 1 is a greater number. And so whenever this is a positive number, it's going to add to the pH. So if you see that the pH is higher, that means that the B must have been higher. And again, that's what this right here tells us. You can also, I just explained what that reads there. Okay? Let's try an example. Here's acetic acid. How will it exist at pH of 7? Which, by the way, is the pH of blood. Well, we first have to know what are the two species, A and B. Okay? You got to know what the two species look like. Acetic acid is an acid. When it acts as an acid, it becomes the conjugate base, the anion. And if we're going to show a charge, we should show the lone pairs on that atom. Very often students are not able to show the correct A and B forms. If you can't do that, then you can't do the next step. The pKa of acetic acid is about 5. Maybe earlier I said 4. Okay, it's roughly about 4 to 5. We'll say 5 here. I ask you at pH of 7. Well, the pH is greater than the pKa. If the pH is greater than the pKa, the basic species will predominate. That means at pH of 7, B, the anion form, will be the predominant form. By how much? By 10 to the 2. So really at equilibrium you have one of these and 10 to the 2, which is 100. This is your equilibrium at pH 7, and you see that you have 100 times more of the B form. That is, it predominates. Okay, there are likely other questions, other examples of this in the workbook, and we may see that in some examples moving forward. This is really just some free information, okay, that may also be in the back. This last page was created later, so I'll probably address this in the back. But please read. From here out, a couple of other miscellaneous problems, illustrations of chemistry. This shows codeine, neutral form. Most drugs are given in an ionic form if possible to make them more soluble in water. As we've mentioned, acid-base chemistry can be used to charge this molecule up. The basic nitrogen will react with the strong acid proton. Electrons move on to chlorine, and we get protonated nitrogen, and then the chloride, the anion, and this is your salt. Okay, charge form, aka salt. I will also call it your ion pair because it's a pair of ions. Can we judge this equilibrium? Well, This goes back to judging equilibrium, which we did before Henderson-Hasselbalch. On the left side, we have the strong acid -5. On the right side, the product side, we have this amine, protonated amine. It has a pK of about 8.2. The weaker acid is favored. That would be the 8.2. And so this is favored by the difference, which is what? 13? 10 to the 13. Huge number. That's like what, 100 billion? That's like 99.9999999% favored. And so what we see here is that a strong acid, okay, a strong acid is typically going to drive your equilibrium, and it's going to protonate something. That's why you want to use a strong acid here. So, just showing that product, looking at the numbers. Always, there's questions to ask anywhere. On the back here is another drug structure. I'm asking you to show the Lewis structure of the mesylate salt. Mesylate is defined down here. Mesylate is the anion of methane sulfonic acid. Okay. If this was HSO3H, which equals H2SO4, that would be sulfuric acid. If we replace one of the H's here with a methyl, we get an acid called methane sulfonic acid. It's still quite a very strong acid. It's just now organic. And so I'm introducing you to a organic sulfonic acid. But you can just use that acid and show the mesylate salt of this drug because it is given as a mesylate salt. Okay, if you can see that arrow there where it says mesylate. That's your acid. What's the most basic atom in this drug? Identify the most basic atom, show your product. Now when you're doing homework like this, you can practice drawing your structure, but you can just sort of modify this structure and show the salt form that way. Okay, free information over here. I'm not going to read it to you. Please read. Okay, we've touched on some of these things. There's picric acid again. We've seen number 4 already several times, including in class. Okay. And then you can go back and work on warm-up questions, pH of 7 or some other pH. Which side of this equilibrium is favored? And then again there. Okay guys, that finishes up this second video on acid-base chemistry. We'll see what type of questions have come up.